Okay, last lecture I gave you an example of how to use temporal discounting and how it might lead to disturbing implications. So the example I gave was you were the manager of a nuclear power plant and you knew there was a potential leak, a leak that was going to cause damage 100 years in the future. And you could either take action now and thereby prevent the leak in future, or you could just let it go and let it affect people in future. And so here was our little cost-benefit table, right? One possible policy, fix it right now, and that was going to cost you $1,000, but it would prevent any costs in future. Or you could do nothing, which would cost us nothing, but would cost $100,000 in future, because it would be quite serious when it occurs in 100 years' time. Now, I made the point that if you go in for discounting, well then all the figures in this column, because they occur later and because they occur 100 years later, need to be discounted. And let's say we used a 5% discount rate. Then what that means is you take these figures and you multiply by 0.95 to the power 100. That is multiplied by 0.95, by 0.95, by 0.95, and so on. Now, obviously 0 times 0.95 to the power of 100, that still equals 0. But if you multiply 100,000 by 0.95 that many times over, well then you get the result. It's around about $590, thereabouts. I'll just indicate that's an approximate sum. But have a look, 590 is less than 1,000, so it turns out the advice is you should do nothing. And this looks prima facie rather disturbing. Well, everything I said last week was correct, but I want to point out there was something a little bit misleading about it, because it's very rare in realistic cases that our choices are simply to fix the problem immediately or do absolutely nothing. What about an intermediate option like wait, let's say 15 years and fix it in 15 years' time? Now, I'm just going to simplify things by assuming it would just be just as difficult to fix in 15 years' time as it is to fix now, so that that $1,000 cost remains constant. Okay? So minus 1,000. But that's not quite the right way to do it, because really, this $1,000 cost, it doesn't actually land on us now. It lands on us in 15 years. Right? And by the logic of temporal discounting then, sorry for the slight mess we're getting here, you then multiply every figure in this column by 0.95 to the power 15. What's that going to equal? Well, I'll tell you, it's kind of in the ballpark of less than $500. So now, when you look at the discounted figures, it's true that still our policy is recommending that a $100,000 cost in the distant future is not such a big deal. It's only $590. But it now looks like the best option of all is to wait 15 years and then fix the problem. So it's not saying you're dooming the people to the very serious cost for sure in the future. It's rather saying it might be rational to wait. You could do then a yet more realistic example. I'm just going to get rid of this mess. It's going to be too complicated. You could say, okay, every year you wait, it gets, let's say, more costly by $100 to fix the problem. But every year we wait, we discount by 5% because we're engaged in this temporal discounting. If you do that, then on the one hand, it's going to keep on going up by $100, but it's going to keep going down by 5%, and it will take longer, but still, it will eventually catch up so that it's sensible to wait. And the advice, I did the sums, it's something like you have to wait for approximately 25 years or so before. So what have I got here? No, more like 50 years. So it's wait for roughly 50 years. So once you've waited for 50 years, of course, the problem is now going to cost around about $6,000 to fix, right? Because 50 times 100 is 5,000, right? So rather than fixing it now and spending $1,000, you spend $6,000 in 50 years, and that's rather than spending $100,000 in effect in 100 years. Temporal discounting, at a rate of 5% anyway, is going to recommend this as the optimal policy.